Good morning, students. So today class we will discuss few problems related on diffraction and also the resolving power of the telescope and microscope. Before going to the topic polarization, we will solve few problems that is based on diffraction and also resolving power of microscope and telescope. So let's take the first problem. A parallel beam of light a parallel beam of light of wavelength 500 nanometer falls on a narrow slit and resulting diffraction pattern is observed. Resulting diffraction pattern is observed on a screen 1 meter away. On a screen 1 meter away, it is observed that it is observed that the first minima observe that the first minima is at a distance of 2.5 millimeter from the center of the screen, from the center of screen. Find the width of the slit. Find the width of the slit. So this is the question. So here a parallel beam of the light of wavelength 500 nanometer which falls on the narrow slit. So here they given the wavelength of the light, that is 500 nanometer, which falls on the narrow slit and resulting the diffraction pattern which is observed on the screen, that is screen is kept 1 meter from the slit. That is, it is observed that the first minima is at a distance of 2.5 millimeter from the center of the screen. So to understand better this question, we will draw the diagram. So this is the single slit and here is the screen. So this is the screen and here is the single slit, right? So the slit width always be taken this slit width as A, where A is the slit width, and here, as like in the Ames experiment, the distance between the slit and the screen is taken as D, right? So here they given the wavelength of the light from, that is, which is falls onto the slit, and then we obtain the diffraction pattern on this screen. So diffraction pattern we will draw here. So this is the diffraction pattern, right? So next, what they given is the wavelength they given and they given observed on the screen 1 meter away. So observed on the screen which is 1 meter away from the slit. Next, it is observed that the first minima. So here the first minima. This one is the central maxima. This one is the central maxima. After central maxima, we get the point here. This one is the first minima. So this point is the first minima, right? So the first minima is at a distance, how much they given? 2.55 millimeter from the central maximum. From here to here, the distance is how much they given? So this distance is 2.5 millimeter. Let's take the distance as x, right? So this is the brief about the question. They given the, here what we are going to find is, we have to find the slit width. That is, here we are going to find the A value, right? So right here the given, so what they are given, the wavelength of the light, that is lambda is equals to 500 nanometer. So if we write in meters, means it becomes 500 into 10 to the power of minus 9 meter. Next, D, the given distance from slit to the screen, that is 1 meter. Next, it is observed that first minima is at a distance of 2.5 millimeter. That one we are taken as x is equals to 2.5 millimeter. If we write in meters, means it becomes 2.5 into 10 to the power of minus 3 meters. Here what we are going to find is, here to find the slit width. So slit width is taken as A. So here we have to find the slit width A. So for that we have to first write the condition. We know that condition for, here they given the distance minimum, then we have to write the condition for secondary minima. The condition for secondary minima is A is equals to n lambda, sorry, theta is equals to n lambda divided by A. This is the condition for the secondary minima. In that secondary minima, they given the first minima value, that is, it is at a distance of 2.55 millimeter from the center of the central maxima. If they given the first minima, then the value of n is equals to 1. Then what happens here? Theta is equals to, n value is 1 into lambda divided by A. That is equals to lambda divided by A. So 1 into lambda is lambda and divided by A. So if you observe here, so this one is the center. So from here to here, this distance they given, here is the angle theta. So if we take on this angle theta from this triangle, if you observe here, if we take theta is very small, then tan theta is equals to opposite by adjacent side. So this one as, or directly we can write. So this one is equation 1. So next, from triangle, theta can be written as opposite side. So this one is the opposite. How much it is? X divided by adjacent side is, the distance is how much? That is D. Right? So here we get the theta from the condition of secondary minima, that is for first minima. Then here from the triangle, from this triangle we can write theta is equals to opposite side, that is x divided by D. So in these two equations 1 and 2, LHS is same. Then we can equate from equation 1 and 2. So we can write x by D is equals to lambda divided by A. So here we are going to find A value, then A is equals to, so it goes to the left side, that is LHS, then it goes to the numerator, then A is equals to lambda D divided by H, right? So A goes to left side, D goes to the RHS, means it goes to the numerator, and X goes to the denominator. Now we know the value of lambda here, we know the value of D here, and we know the value of X, then we can find the value of A, right? So if we substitute here, A is equals to lambda is 500 into 10 to the power of minus 9 D, they given 1 meter into 1 divided by x value 2.5 into 10 to the power of minus 3. So if we simplify here 25, it becomes 5000, or 5 divided by 2.5, or 50 divided by 25. So if we simplify here, we get the value 10 to the power of minus 3 goes to the numerator, it becomes 10 to the power of minus 6. Then if we simplify, we get 2 into 10 to the power of minus 4 meter. So here 2 0 shift means it becomes 10 to the power of minus 7. Minus 7 plus 3, it becomes minus 4. So 50 divided by 25, that is 25 and the 25 twos are, that is 2 into 10 to the power of minus 4 meter, or this can be written as 0.2 millimeter. So 2 divided by 10, we get 0.2 into 10 to the power of minus 3, that can be written as millimeter. So this is the final answer, 0.2 millimeter, right? So if we write the diagram here, then we can get the clear picture of this question and can be simplified very easily, right? So this is the first question. Next, move on to the second one. So next question is yellow light of wavelength, yellow light of wavelength 6000 angstrom illuminates a single slit of width a single slit of width 1 into 10 to the power of minus 4 meters. Calculate the distance between two dark lines on either side of central maximum, when the diffraction pattern is viewed on the screen kept 1.5 meter away from the slit. Right, this is the second question. So in this question they given yellow light of the wavelength 6000 angstrom illuminates a single slit of width 1 into 10 to the power of minus 4. Calculate the distance between two dark lines on the either side of the central maximum when the diffraction pattern is viewed on the screen kept 1.5 meter away from the slit. So here what we are going to find out is they are given the wavelength. First they given the wavelength, that is 6000 angstrom, and also they given slit width, the value of A 1 into 10 to the power of minus 4 meter, and next they given capital D, that is distance between slit and the screen. So if we write here, given lambda is equals to 6000 angstrom, that is 6000 into 10 to the power of minus 10 meter. Next, split width they given A is equals to 1 into 10 to the power of minus 4 meter. Next, they given capital D is equals to 1.5 meter. So in the question, what we are going to find is, so this one is the first minimum. First minimum nothing but the dark region. So here we get the first minimum. Here also we get the first minimum on either side. So this represents what, the dark region. So here what we are going to find is, we are going to find the width of the central maximum. They are not directly asked to find the width of the central maxima. They ask for the distance between two dark lines on either side of the central maxima. So this one is the central maxima, this one is the central maxima. So either side means on the top above side we have first minimum, and in the bottom side also we have one first minimum. We have to find the distance between these two first minimas. Then similar, first we have to write the condition for minimum. So condition for minima is theta is equals to n lambda divided by A. So here the condition which we are going to find is for the first minima. Then n value becomes n is equals to 1, then theta is equals to lambda divided by A. So for theta we get only this value, that is half value. Then we need full value. So from this triangle if we write, so this one is the equation 1. So from this triangle if we consider this one as x, then theta is equals to x divided by d. So we need total this distance, that is if we consider overall this distance, then what happens, it becomes theta is equals to 2x divided by d. Right? Now if we substitute here it becomes theta is equals to x divided by d. So here for first minima it is lambda by A. Here also we have first minima lambda by A. Then here we get theta is equals to 2 lambda divided by A. So now if we substitute this value, then x divided by d is equals to 2 lambda by A. So right, we need the x value, then this can be written as x is equal to 2 lambda capital D divided by A. So this is the formula for the width of the central maxima. If we remember this formula, we can directly substitute this formula. By using this formula, we can directly substitute the values and then we get simplified, right? So this is the formula for the central maxima, that is width of the central maxima. So here we know the values of lambda, d and a, then we get x value. So if we substitute, x is equals to 2 into, so lambda is 6000 into 10 to the power of minus 10 into the value of d, they given 1.5 meter whole divided by slit width 1 into 10 to the power of minus 4. So 2 into 1.5 we get 3. Here we have 3 zeros, it becomes 10 to the power of minus 7. It minus 4, if we shift to the plus, then we get 10 to the power of We write here 3 into, that is 2 into 1.5, we get 3. Next 6 into, here with 3 zeros, then into 10 to the power of 10, that is we can write 10 to the power of 3 minus 10. So these 3 zeros are written, can be 10 to the power of plus 3, 10 to the power of minus 10. This 10 to the power of minus 4, if it goes to the numerator, it becomes plus 4. So 3 plus 4, 7. 7 minus 10, 10 to the power of minus 3. So 6 3s are 18 into 10 to the power of minus 3 meter, or it is 18 millimeter. Right? So this is the final answer. That is, we need to find the x value. That is the width of the central maximum. Or we write, this is the formula for width of the central maximum. X is equals to 2 lambda d divided by a, where a is the slit width. So if we know this formula, we can directly substitute the values of lambda d a and simplify, we get the value, right? That is 80 millimeter. So if we know this formula, we need not to solve up to this one. We need not to find by simplifying like this. So directly we can write the formula and substituting the values, then we get the answer. So we have to note this one directly. That is the formula, width of the central maximum, or they may ask the distance between the first minimas. So if they ask the distance between the first minima, means here is the first minima and here is the first minima, that distance is equal to the width of the central maximum. Right? So this is the second question. So move on to the third question. So next third question. In a single slit experiment, in a single slit experiment of diffraction a slit of width A is illuminated by the red light of wavelength 650 nanometer. For what value of A will, for what value of A will. So here A is this slit width, A will. So in that first one, the first minimum, fall at an angle of diffraction an angle of diffraction of 30 degree. So in the second one is the first maximum fall at an angle of diffraction of say 30 degrees. So in this question, there is single slit, experiment of diffraction, slit width we have to find. That is, we have to find the slit width, that is A, which is illuminated by the red light of the wavelength 650 nanometer. So they given the wavelength of the red light, that is lambda is equals to 650 nanometer. So we need to find the A. Here they given the two conditions, that is for first one. For first minima falls at an angle of diffraction 30 degree. That is the given angle theta. We need to find the first minima. So at what distance the first minima will fall from the central maximum? So from here to here, they given the theta. For that theta, we need to find the slit width, that is A, and also for the first maximum. So here is the first maximum. For that also they given angle theta is equals to 30 degree. So if we write the given lambda is equals to 650 nanometers, that is equals to 650 into 10 to the power of minus 9 meters, and we need to find A. Then the given angle theta is equals to 30 degree. Right? For solving first one, first we have to write condition for minimum or secondary minimum, that is theta is equals to n lambda divided by A. So they given first minimum, then value of n becomes 1, that is n is equals to 1 for first minimum, right? So they given angle theta, that is angle theta is 30 degree. So here we can write this one as sine theta. So in the derivation we taken sine theta, that is a sine theta is equals to n lambda, that is the condition for the minimum. If n is equals to 1, then a sine theta is equals to lambda is the condition for the first minimum. Then we need to find a, then a is equals to n lambda divided by sine theta. That is they given the angle 30 degree. So if we substitute n value 1, lambda value 650 into 10 to the power of minus 9 divided by sine 30 degree. So if we substitute, that is 650 into 10 to the power of minus 9, the value of sine 30 is 1 by 2. So next 650 into 2. So here we get 0 to 5 are 10, 12 plus 1, that is 1300 into 10 to the power of minus 9. If we shift 3 digits, then it becomes 1.3 into 10 to the power of minus 6 meter. Or we can write, here I will write A is equals to 1.6 micrometer. So this one is the slit width for the first condition. For first minimum, n is equals to 1, then they given the angle theta. So from that we can find value of A, that is 1.6 micro means 10 to the power of minus 6 meters. Right? So similarly for the second one, condition for maximum, that is condition for secondary maxima. If we write the condition, then sin theta is equals to n plus 1 by 2 into lambda divided by A. So here also they given for first maxima which falls at the angle of 30 degree, then for first maxima n value becomes 1. Right? For first maxima, n value becomes 1. So we need a. Then a is equals to n plus 1 by 2 into lambda divided by sine theta. So we know the value of n, that is 1 plus 1 by 2 into 650 into 10 to the power of minus 9. Similarly, here is sine 30 degree. So here if we take LCM, it becomes 3 by 2 into 650 into 10 to the power of minus 9 whole divided by 1 by 2. So these two in the denominator, 2 divided by 2 get cancels. Next 3 into 65. So 3 5s are 15, 18, that is 1950 into 10 to the power of minus 9. So this can be written as 1.95 into 10 to the power of minus 6 meter, or we can write 1.95 micrometer. So this is the final answer for the first maxima, which falls at the diffraction at 30 degree. For this we have to write the condition. So by using the condition for minima and maxima, then they given the values lambda and theta. From that we can find the value. So it is at 1.6, maxima will be at 1.95 millimeter. So this is about the problems regarding on the diffraction. So next problem based on the resolving power. The diameter of the objective, the diameter of the objective of a telescope is 1.2 meter, is 1.2 meter. If the wavelength of light used, if the wavelength of light used, if the wavelength of the light used is 546 nanometer, calculate the limit of resolution, calculate the limit of resolution of telescope. So here we need to find the limit of resolution of the telescope. So they given the diameter of the objective. So right here. So given is diameter of the objective. In case of telescope, we taken that one as 2a, that is equals to 1.2 meter. Then a becomes a is equals to 0.6 meter. Next, the wavelength of the light used, they given lambda is equals to 546 nanometer into 10 to the power of minus 9 meter. We need to find the limit of resolution of a telescope. For that, limit of resolution of a telescope, that is we taken delta theta that is equals to 0.61 lambda divided by A. So this is the formula for the limit of resolution of a telescope, that is delta theta is equals to 0.61 lambda divided by A. So 0.61, we know the value of lambda, that is 546 into 10 to the power of minus 9 divided by the value of A is 0.6. So 0.6 into 0.61, we get 1.01 into 546 into 10 to the power of minus 9. Then here 1 point we get 555.6 into 10 to the power of minus 9. So if we shift means we get 5.55 into 10 to the power of minus 7. That is delta theta. That is limit of resolution. Here we get 5.55 into 10 to the power of minus 7. So the unit is radians. Right? So this one is very simple. Just we know the formula here. Limit of resolution is delta theta is equals to 0.61 lambda by A. They given the lambda value and A value, substituting and simplifying, we get limit of resolution, that is theta. So in this question, if they may ask continue for the resolving power, so resolving power of the telescope is equals to 1 divided by delta theta, then 1 divided by 5.55 into 10 to the power of minus 7, then we get the resolving power of the telescope. Move on to the next question. Fifth, the angular separation between two stars is 4.8 into 10 to the power of minus 6 radians when they are just resolved. When they are just resolved by a telescope, find the resolving power, and radius of the objective, of the telescope wavelength of light is given. Wavelength of light is 650 nanometer. Right? So here they given the angular separation between two stars is 4.8 into 10 to the power of minus 6 radians when they are just resolved. Nothing but they given the limit of resolution value delta theta, that is equals to 4.8 into 10 to the power of minus 6 radians. So we need to find the resolving power and radius of the objective, that is A value. They given the wavelength of light. So here what they are given means they given delta theta, that is equals to 4.8 into 10 to the power of minus 6 radians, that is theta or delta theta. They given limit of resolution. They mentioned that when they are just resolved by a telescope. So delta theta is the limit of resolution of the telescope. And also they given wavelength lambda is equals to 650 nanometer, that is 650 into 10 to the power of minus 9 meter. So we need to find first the resolving power. So resolving power, that is equals to, it is the reciprocal of the limit of resolution. Then we can directly write 1 divided by delta theta. So we know that the value of delta theta 1 divided by 4.8 into 10 to the power of minus 6. So 1 divided by 4.8 value, that becomes 2.083 2.083 into 10 to the power of 5 into 10 to the power of 5. So this gives the resolving power, right? So this gives the resolving power. That is, it is the reciprocal of the limit of resolution. So next, one more, we have to find the radius of the objective. Also we know the resolving power of the telescope, that is equals to 0.61 lambda divided by A. So this is the formula for the resolving power of the telescope, 0.61 lambda divided by A. So here we know the value of lambda, we know the value of resolving power, then we can find the value of A. So resolving power is 2.083 into 10 to the power of 5, that is equals to 0.61 into wavelength 650 into 10 to the power of minus 9 whole divided by A. So if A shifts to the LHS, then this value goes to the denominator. So by using calc, if we simplify, then we get the value of A, that is equals to 8.86 into 10 to the power of minus 2 meter. So here the resolving power, this one is for the formula of limit of resolution. So this can be written as, here this is the delta theta, limit of resolution is equals to 0.61 lambda divided by A. So we need to substitute the value of 4.8 into 10 to the power of minus 6. Then we get A value is equals to 8.86 into 10 to the power of minus 2 meter. So this is the formula for the limit of resolution, not for resolving power, limit of resolution, right? So these are the problems which is based on the diffraction, and also the problems which are based on the resolving power of the telescope and microscope. So from the next class we will discuss the new phenomenon, that is phenomenon of the polarization. So how it happens we will discuss in the next class. Thank you.